All right. Hello, class. Hope you guys are doing well. Um, so this is our last lesson for uh, CHL. Um, I'm going to give you tomorrow to work on the quiz. Remember, the quiz is due tomorrow. And then I should have the grades wrapped up by Monday, probably. Um, and like I said, I'll be uh, volunteering at some of the senior checkout activities and some of that stuff. So hopefully I'll see some of you. And I'm probably gonna do some kind of a Zoom meeting next week. So maybe we could get together or something like that. Um, might be kind of fun. Um, I don't think any memes have been submitted for the meme review. So if you want a meme review to happen, submit some memes. Um, all right. So thank you to everyone who's watching. Hey Fu, hey Nick, hey Justin, hey James. So let's get right down to it. Um, what I wanted to talk about is today is conservation of form momentum. Okay, so basically the total initial momentum equals the total. Hey Rowan, final momentum. Okay, so what does that mean in terms of equations? It means what you do, Hazel. What you do? Hazel's overheating. So what it means is that if we look at the momentum, what is the total initial momentum? Well, it would be gamma mc gamma mv plus gamma mc gamma mv plus dot dot dot. So this is gamma 1 m1. This is gamma 2 m2, and so on. So you just add up the momenta of all the particles, okay? Plus any photons. So maybe you have HF over C, where this is F1, HF2 over C, plus or minus, plus dot dot dot. All that has to equal a constant, okay? And so the cool thing about this is that it kind of unifies conservation of momentum, which we already knew about, and conservation of energy, which we knew about, into one conservation law. So energy is conserved. That's the top row, the time component of this. And momentum is conserved. All right? So that's the conservation of form momentum. And this is good during collisions. So we're going to do two examples today with collisions. So for our first example, let's suppose two identical particles okay, with mass let's say with mass m and speed v, traveling in opposite directions, collide and merge to form a new particle. What is its mass? Now, if we used non-relativistic logic, the answer would be very simple. It would be 2m, right? Because it's just, if you take something that weighs 1 pound and you add to it another thing that weighs 1 pound, you get something that's 2 pounds. But that's not going to be true in special relativity because, as we know, mass is a form of energy, and so is kinetic energy. So some of that kinetic energy of the particles basically can become mass. Okay? So we have, so basically the picture of what's happening is we have two particles. Okay. And they collide and they make a superparticle. Okay. So what is the initial momentum? The initial momentum is gamma mc, gamma mv. So this is the particle that's traveling to the right because its space component of the momentum is positive. Plus, and then the other particle is gamma mc minus gamma mv. So this would be the momentum of the one that's going in the opposite direction. Okay? The gammas are the same because remember, gamma depends on velocity squared. Okay, so if you're going to the left or to the right, your gamma is going to be the same. And then those merge to become another particle, which is just a single particle. I'm going to call the mass of that m squiggle, and I'm going to call its velocity v squiggle, and I'm going to call the gamma that would be calculated from that velocity gamma squiggle. Okay? So, if I complete the addition, this is just an addition of two vectors. So I add these two together, I add these two together, right? So the initial momentum is going to be 2 gamma mc 0. And that equals gamma squiggle m squiggle c gamma squiggle m squiggle v squiggle. Okay? So, in particular, the bottom row of this equation says that 0 equals gamma squiggle m squiggle v squiggle. Now, both gamma and m are not equal to 0. Okay, gamma is always greater than 1. The mass of this particle isn't equal to 0. So what that says is that v squiggle equals 0. Okay? So and that would make sense if you have two things that are identical and they're going in opposite directions and they collide, it's going to be at rest afterwards. Okay? Now, in particular, if the velocity is 0, then that means that gamma squiggle is going to be 1. Because remember, the formula for gamma is 1 over the square root of 1 minus v squared over c squared. So if v equals 0, then this term drops out, and then the denominator is just square root of 1, which is 1. So you have 1 over 1. Okay? So that's what the bottom equation says. It says this information. Now we look at the top equation, and it says 2 gamma mc equals gamma squiggle m squiggle c. So that means that, in particular, the c's cancel out. And then I know that gamma squiggle is equal to 1. So I just get m squiggle equals 2 gamma m. So that would be my answer. Hey, Zach. Hey, Alex. Now, it's interesting. So if these two particles are going slowly so that they could be considered non-relativistic, then gamma is going to be approximately 1, and so we would get that the mass of the composite particle was approximately 2m, which is the non-relativistic logic. So basically, special relativity has to give the same predictions as regular physics in the limit of the things traveling at non-relativistic speeds, okay? So you're always looking, as a sanity check on your equations, you're always looking to see how do they merge into everyday physics in the limit that the speeds are small compared to the speed of light, okay? So so I'm going to do one more example. Maybe we'll end it off with a three-way collision. So let's do a three-way collision. We've got a particle of mass m at rest. Okay? We've got a photon headed rightward with frequency f1. We've got a photon headed left with frequency f2. They all collide. And make a massive particle. What is its speed, which we'll call v squiggle, and what is its mass, which I'll call m squiggle. So if I were to draw this out, we've got a particle in the middle. We got a photon headed this way. So this is m. We got this photon which has frequency f1. We got this photon which has frequency f2. They collide and they make a composite particle m squiggle. Now, again, in non-relativistic theory, light doesn't have a mass, so this wouldn't change the mass at all, okay? But when we talk about relativity, we have to worry about these things. Okay, so I'm going to quickly write out the law of conservation for momentum. So it would be mc0. So this is the particle of mass m that is at rest. Remember, if it's at rest, then v equals 0, and therefore gamma equals 1. So the gamma is 1. We have mc0 there. And then we have hf1 over c plus hf1 over c. So this one has a positive space component because it's traveling to the right. And then we have plus hf2 over c minus hf2 over c. So this one has a negative space component because it is traveling to the left. And then this is going to make, depending on which frequency is greater, it's going to either be going to the left or the right, because if this one has a greater frequency, then this photon has more momentum than that photon, and so the net result will be something that travels to the right. So let's just assume F1 is greater than F2, okay? And let's define delta F as F1 minus F2. How about that? That'll make it easy. Okay. So then we have this is equal to the composite particles for momentum. So that's going to be gamma squiggle M squiggle C, gamma squiggle M squiggle V squiggle. Okay? So performing the addition, let's also define F bar as the average of the two frequencies. So F1 plus F2 over 2. Okay? So what do I get when I add the top row? I'm going to get MC plus H F1 over C plus H F2 over C equals gamma squiggle M squiggle C. All right? Which I could rewrite as MC plus H F bar over C equals gamma squiggle M squiggle C. All right. So this is one of my equations that I have to solve. And then my other equation would be adding the bottom rows. So I would have 0 plus H F1 over C minus H F2 over C equals gamma squiggle M squiggle V squiggle. Okay. Which can be written as H delta F over C equals gamma squiggle M squiggle V squiggle. So this is our second equation. All right. Now what I can notice here is that V squiggle over C equals that's going to equal gamma squiggle M squiggle V squiggle over gamma squiggle M squiggle C. So notice how if I divide this by this, I can get the velocity, okay? Now, using the bottom equation, I could write this as H delta F over C. And the bottom one I could write as MC plus H F bar over C. All right? So then I could multiply both sides by C over H. Like that. So I'm going to get V squiggle over C equals delta F over MC squared over H plus F bar. So there, that's the answer. That's the answer for the velocity. Okay. Now we have to figure out what is gamma squiggle. And this one's going to be not so fun. Okay. So we can get some fairly nasty formulas. So I'm actually going to go to a different page. I'm going to do this, I think. So gamma squiggle would be 1 over the square root of 1 minus V squiggle squared over C squared. All right. So I got to square this quantity. So I'm going to get V squiggle squared over C squared is going to be delta F squared over MC squared over H plus F bar, that quantity squared. Then I have to do 1 minus that. Which is going to be squared over H plus F bar 1 quantity squared minus delta F squared over mc squared over h plus F bar quantity squared. Okay. Then I got to do the square root of that. And then I got to do 1 over that to the negative 1 to the negative 1. So that means that gamma squiggle equals mc squared over h plus F bar over the square root of mc squared over h plus F bar quantity squared minus delta F squared. So that's nasty. That's real nasty. Oh my gosh, and I just realized that right here I forgot a 2. Because this would be twice the average. Oh. So that should be 2. Which means, it's not that big of a mistake. Which means this should be 2, which means this should be 2. Which means this should be 2 and that should be 2. Okay? So now, notice that if I go to this equation here, I could write m squiggle equals mc, and this should be 2. This should be a factor of 2 as well, because F1, I forgot to include the extra factor of 2. So I have mc plus 2 hf bar over c over gamma squiggle c. All right, and then I just plug in that formula for gamma squiggle, and I have my answer for the mass of the particle. Okay, so that's not very enlightening. I could work out the algebra of it and get some answer, and we could try to take some limits for what if this happens, or what if this happens, et cetera, et cetera. But I don't think it's very important. The important thing is the general concept of conservation of energy momentum. So photons can merge to create mass, to add to mass. Mass can disappear and create photons, okay? Because energy and mass are equivalent to each other. So that's pretty cool. One thing you can actually do is you can even, if you had intensely powerful lasers that are shooting photons at each other, you could make the photons collide and actually create a black hole. If the frequency of the photons is high enough, or if there are a great enough number of photons, you could create a black hole. A black hole created by photons is called a Kugelblitz. So check it out, Kugelblitz, K-U-G-E-L blitz. All right, so that's my very brief introduction to special relativity. If this interests you, I would recommend that sort of the next step would be to look at how does Newton's second law of motion generalize to objects moving at relativistic speeds. And there's actually a very natural generalization of Newton's second law, and it's pretty cool. So, hope you guys have a wonderful afternoon, and good luck on the quiz, and hopefully I'll see some of you at the senior checkout, and maybe at a Zoom